Hello guys, welcome to this small video. This is a review video about the MN rule or the product rule. Quickly, just a reminder, if we have M elements, A1 until AM, and N elements, B1 until Bn, we can make M times N pairs containing one element from each group. This is the definition of class, so nothing new here. The MN rule can be extended to any number of groups with any number of elements. So the classic example is the dice example. If we have two dice, then we have 6 times 6. If we have 3 dice, then the same thing. If we have 2 coins, 2 outcomes per coin, those number of outcomes, so nothing new here. The thing that it's new is this problem. Let's say that we have this company, the Kentucky Power and Light Company, and they are trying to increase their generating capacity for one of its plants, and that project is divided into 2 stages. The first stage is the design stage, and the second stage is the construction stage. So let's say that you are part of the management, but you are not able to predict the exact time required to complete the whole project, or each stage is the same thing. But you go to some historical analysis, and similar projects have completion times for the first stage of 2, 3, or 4 months. And for the second stage, they have completion times of 6 or 7 or 8 months. So you, as the part of the management, set a goal of completing this project in 10 months. So let's remember, stage 1 has been completed before in 2, 3, or 4 months, and stage 2 in 6, 7, or 8 months. So the question is, in how many different arrangements of time can the new project be completed? Well, of course, we use the MN rule, and we see that for the first stage we have 2, 3, or 4, that is 3 possible outcomes. And for the second stage is the same thing, we have 6, 7, or 8. So we have a total of 9 possible arrangements of time. So now let's use some notation. Let's say that this pair to 6 means that we took 2 months in the first stage and 6 months in the second stage. Or we can have like 3, 6 or 4, 8 or whatever. Any combination of times in the first stage with the second stage. So that means that in our omega, in our sample space, we're going to have 9 different times. So we're going to have 9 pairs like this. So notice one more thing. If we complete the first stage in 2 months and the second stage in 6 months, then our whole project is going to be completed in 8 months, right? If we spend 3 and 6, then in 9, 8 and 4 and 8, sorry, then in 12, and so on. So we know that the least amount of time that we can spend in our project is 8 months, and the most we're going to take a year, 12 months. So let's use this pair notation to denote the time in the first stage and in the second stage. So now some interesting questions arise. In how many of the possible outcomes is the goal of completion in 10 months exactly satisfied? So from all the pairs that we can make, how many of those add up to 10 months? And the second question, let's assume that all the pairs are equally likely. 2, 6 and 3, 6 and all of those are equally likely. So what is the probability that KPL, the Kentucky Power and Light Company, will finish its project in 10 months or less? So one way to think about this is algebraically. I mean, only writing products and multiplications and adding all the times. Another way to think about this is with drawings. So let me see if I can hook you up with a very nice drawing. Sorry. So there, in this drawing, we can see that this dotted line, everything to the left, represents the first stage. So we can spend either 2 months or 3 months or 4 months. This piece here represents the time, the possible times for the second stage. So we can spend 6 months, 7 months or 8 months. But all of these can be paired up with 2 months of the first stage, and all of these can be paired up with 3 months of the first, and the same thing with 4 months. So the question some of you asked in class is why we multiply 3 times 3. Well, this is a graphical answer for that question. All the stages, all the options for the second step, for the second stage of the project, have to be paired up with every option in the first stage. So of course we're going to end up with 3 here, 3 here, 6, and 3 here, 9. So we have all of these pairs to 6, to 7, to 8, and so on. If we add all of this, then we have 8 months, 9, 10, 9, 10, 11, 10, 11, 12. So to answer the first question, the question in blue, in how many of those the goal of completing the project in 10 months is exactly satisfied? Well, of course, here we have 1, 2, 3. So let's call this question A. So for question A, in exactly 3 of all of our outcomes, we're going to complete it in exactly 10 months. Now for the second question, let's call it question B, we want to finish in 10 months or less. So of course we have to count all of the outcomes that have 10 or less. So of course we're going to have the first one, it's almost non-visible, sorry. The second, the blue ones, of course, because those are 10, plus this one with 9, and that's it. So we have 1, 2, 3, 4, 5, 6. So the answer, the probability, let's write it like this. In 10 months or less, let me write this minus sign to represent less. That's not proper notation, but don't worry about that, we will get there. Is 6 out of 9 possible outcomes, and of course we can simplify this fraction, so that is 2/3. So the probability of ending our project or finishing our project in 10 months or less is something like 0.66 or something like 66% probability. So this is kind of a very interesting problem. It's a little bit more grounded to some real applications, not just dice and coin tosses. So thank you guys, I hope you enjoyed this. See you later.